Section 8.3 talks about trigonometric substitution. So basically there are three cases that we're going to investigate where we use trig substitutions. This procedure for trig substitution came from your textbook. The first thing that they suggest is to write down the substitution for x. So there's going to be a couple of choices. You're going to either let x be a times tangent theta, or x is a sine theta, or x is equal to a secant theta. And then, as when you do any substitution, you take the derivative and find dx. Second, substitute the trig expression and the differential into the integrand, just like you do with regular substitution. And then you integrate. Now, in the end, you're going to end up with a theta in your problem, and you need to remember that the problem started with x's in it. So at the very end, you're going to have to move from the angle theta back to an x value. And we'll show how to use reference triangles to reverse that substitution. So let's take a look at our three cases. Case 1 is when you have an a squared plus an x squared. When you have a squared plus x squared, you're going to let x be equal to a tangent theta. So that means you need to square root that a squared to find out what a is equal to. And then take derivative. So the derivative of tangent theta is, of course, secant squared theta d theta. Okay, let's go ahead and do this example that's given. So let's start off by investigating what a is. A, since it's the square root of this, would be equal to 2. That means that I'm going to let x be 2 tangent theta, because I see that I have a squared plus x squared scenario. The derivative of this is 2 secant squared theta d theta. Let's go ahead and use this information in order to substitute into our integral. So now I have the integral of the dx is on the top, so let's put in 2 secant squared theta d theta. And on the bottom I have a square root of 4 plus, and I need to square this x. Let's simplify this. I'm going to take the 2 and put it out in the front. And on the inside of this radical, I have a 4 plus 4 tangent squared theta, because I am squaring. I think you'll see here on the bottom that there is a 4 in common, which we can factor out. And when we factor it out, we can square root it, and it becomes a 2. So that 2 is on the bottom. And since I factored out the 4, I'm now left with the square root of 1 plus tangent squared. So of course those 2's in the front cancel, and I know 1 plus tangent squared is secant squared. Square root of secant squared is secant. So when I cancel the secant from the bottom with the secant squared from the top, I end up with this. And this is one of those new integrals that we discussed back about a few weeks ago, where we said this is a new one that we should memorize because it keeps popping back up. And they say, oh yeah, look at this, voila! Integral of secant is ln of secant plus tangent. So they don't really expect you to do out that integral of secant longhand anymore. Now, this is what I was talking about. Your answer that you have right here has thetas in it, but the original problem has x's in it. So we have sort of an issue here because I need to replace my thetas with x's. So let's go ahead and figure out what we need to do. So first of all, I know that tangent theta is equal to x divided by 2. So I can substitute that right in here. But I don't know what secant theta is. So let's go ahead and make a little triangle. I'm going to make a right triangle because it makes me feel better. Because drawing is so fun. And I know that tangent is opposite over adjacent. So if this is my theta, this would be x and this would be 2. And I know that 2 squared plus x squared equals that hypotenuse squared. So the hypotenuse is the square root of 4 plus x squared. That allows me now to find secant of theta, because I know that secant of theta is the reciprocal of cosine. So it would be the adjacent, it would be the hypotenuse, reciprocal of cosine, hypotenuse over adjacent. And so now my final answer would be ln absolute value square root of 4 plus x squared over 2 plus x over 2 plus c. Let's go on to case 2. Case 2 is when you have an a squared minus x squared. And in this case, you're going to let x be a sine theta. Again, notice that a is going to be the square root of the a squared. And just like any substitution, you take derivative and it comes out to be a cosine d theta. So let's now try this with this example. So in this example, I can see that my a is going to be 3. So I'm going to let x be 3 sine theta, which means that dx would be 3 cosine theta d theta. So now I can go ahead and substitute things into this integral. So now I have the integral of, I'm going to square this x. I'm going to put in dx. And on the bottom, I have a square root of 9 minus, and I'm going to put in the x and square it. Okay, let's do some simplifying. So let's see, I have integral of, this is make 9 times 3, which is 27. And I have a sine squared theta, cosine theta, d theta. And on the bottom, I have a 9 minus 9 sine squared theta. So I can see that I can factor out a 9 on the bottom. And when I square root that 9, it becomes 3. And so when I factor out the 9, I'm left with 1 minus sine squared, which of course is cosine squared. And I can cancel one of the cosine squareds. Whoopsie, I lost my square root. How dare I? Put the square root back, put the square root back. I'm such a goofball. And of course, this square root of cosine squared is cosine. So the two cosines cancel, actually, because I have a cosine on the top, and the square root of cosine squared on the bottom cancels. So now the bottom is actually gone. Woohoo! So now I'm back to the good old case of an even exponent on sine. So I'm going to go ahead and change that over to the double angle formula. And I have 9 integral of a half minus a half cosine of 2 theta that would be 9 halves x. Oops, not x. We're in thetas now. Theta. And of course, the antiderivative of cosine is sine. Don't forget to divide by the derivative of the angle, because again, the chain rule is in reverse. And don't lose your 9. It has to be distributed to everybody. So that would be great, except that we didn't start with thetas. We started with x's. So again, we have to switch back from thetas back to x's. So one of the things I notice is I have defined that sine theta is equal to x divided by 3. But here I see I have a sine of 2 theta. That's no good. I need to change that to the double angle formula. So sine 2 theta is 2 sine theta cosine theta. Now I'll be able to replace that sine theta with x over 3. I also know that theta is equal to sine inverse of x over 3. So that would allow me to replace my theta. And so the only thing left to replace for thetas is cosine theta. So again, I just feel better when I draw a triangle. And I know that sine is opposite over hypotenuse. So using the Pythagorean Theorem, I can find out that this side is 9 minus x squared. And that tells me that cosine theta would be adjacent over hypotenuse. And that would allow me to replace this. Finally, doing all the replacing, my theta is sine inverse. I can cancel the 2 and the 4 here and make 9 halves. Sine of theta was x over 3. cosine theta was square root of 9 minus x squared over 3. And then finally do a little simplifying here. I can cancel. And that's my final answer. Case 3 is when you have x squared minus a squared. In this case, you let x be a secant theta, and of course, take derivative in order to do your substitution. First thing I notice about this particular problem is that it's not x squared minus a squared because there's a 25 here. So let's go ahead and factor that 25 out, which would make this 4/25. And the square root of 25 is 5. So I can take that right on out of there, and that will help me to make the problem look like x squared minus a squared. I can then see that my a is 2 over 5. So I'm going to let x be equal to 2/5 secant theta, and my dx would be 2/5 secant theta tangent theta. Let's go ahead and do a substitution. Okay, so my dx I have a 1/5. My dx is 2/5 secant theta tangent theta d theta. On the bottom, don't lose your square root. I seem to lose my square roots. I think I don't like them because they look sharp and pointy. Anyway, keep that square root there. Okay, so on the bottom I have a square root of, and my x is 2/5 secant theta, so I'm going to have to square that. And now I've replaced all my x's. I'm going to go ahead and bring this 2/5 out here. So now I have 2/25 secant theta tangent theta d theta. And on the bottom I have a square root. And I'm going to take the 4/25 because that's what that is squared. I'm going to factor it out. So I'd be left with secant squared theta minus 1. So in the front I have a 2/25. The 4/25, when I square root it, becomes 2/5, which means I'm actually going to multiply by 5/2 because you're dividing by a fraction. And secant squared theta minus 1 is tangent squared theta. And square root of tangent squared theta is tangent theta. So we can see that it is going to cancel with the tangent theta from the top. So let's go ahead and simplify these fractions. My 2 tangent thetas are going to cancel. And again, I end up with the magical formula. Integral of secant is ln of secant theta plus tangent theta. Again, I can't leave my answer like this because I started with x's and now I'm in thetas. So what do I know? One of the things that I know is that secant theta is equal to 5/2 x or 5x over 2. I know that secant is a hypotenuse over an adjacent. So if I draw a triangle with a theta, my hypotenuse would be 5x, my adjacent would be 2. And when I use Pythagorean Theorem, I find out that the other side is 25x squared minus 4. That means that the tangent theta that I need in the final answer would be opposite over adjacent. So now I can take that information and write my final answer. My secant is 5x over 2, and my tangent is square root of 25x squared minus 4 over 2. Okay, there's 2 problems here for you to try. I know, they look kind of crazy. They are crazy indeed. If you're having problems with these, I will be covering this on Friday. So definitely pop onto the Zoom call on Friday and I can help you through it. All right. Have fun. Be kind to people. See you later, alligators.